Let's bring up this document that your mom sent me. Where do you want to begin?
Let's just begin with like the first question on here.
Okay. So it says graph it and then state the info. But really the secret to these is to stating the info first. And then you'll be able to graph it. Okay. What are we looking at? What kind of graph is this?
A linear one.
Hyperbolic.
Was it?
Hyperbolic. A hyperbola looks kind of like this. A hyperbola tends to look like this. Okay? So we're expecting a graph to look kind of like this, just like this next one. What kind of function is that? What shape is that?
That's a quadratic.
Which means it's a parabola. And either it's going to look like this or it's going to look like that. Okay? All right, so let's go back to the first one. Let's start with vertical asymptote, because the way you do these is you draw your grid based on the vertical asymptote and the horizontal asymptote. Where's the vertical asymptote?
The vertical asymptote, would that be derived from the bottom?
Correct. Whatever makes that 0. What value of x makes that division by 0?
-2.
Okay. So we're going to draw our vertical asymptote. And incidentally, the vertical asymptote is the equation of a line. Hold on. Strange things are going on with my computer today. Hopefully, okay, here we go. So it's x equals -2. About the horizontal asymptote.
Right. The horizontal asymptote is just +1.
Actually, it's 0. Y equals 0. Whenever the denominator has a higher degree exponent than the numerator, the asymptote is always y equals 0. I could have something like this. Well, 3 is bigger than 2. There's an asymptote here of y equals 0. And in the problem we're doing, there is no x. So it's x to the 0 in the numerator. So the horizontal asymptote is the x-axis, which is the line y equals 0. What's the domain?
Would it be, let's see, the domain would be, what you call it, a -2 to infinity?
The domain is all allowable values for x.
So I guess -infinity to 2 and then union.
Okay, there you go. It's -infinity to -2, because it can't be -2, in union with -2 to +infinity. That's all of the allowable values for x. Another way I could have said it would be all real numbers except x cannot be -2. Okay, now to sketch it, I'm going to draw, remember that hyperbolic function I drew over here?
Yeah.
Well, I know it's going to look like that. It's just I'm going to do it about these grid, this new grid system. I'm not going to do it about the x and y axis. I'm going to do it about my horizontal and vertical asymptote. So I got two ways that this might look. One would be like that. For a moment, we're talking about just this part of it. I'll deal with the +1 in a second. Okay?
Okay.
We're going to either, it's going to look like that, or it's going to look like this. In other words, it's going to be in either quadrants 1 and 3 or 2 and 4. How can I tell which one it is?
Aren't the ones that are like not negative always on the top right and bottom left?
Pick a number for x. Easy number. Tell me what y is. Pick 0. Nice easy number for x. What is y when x is 0?
Would it be 1 or 2? Sorry.
It's 2. Okay. Well, x is 0 right there, and y has to be 2. So that point is on the curve, and that basically tells me which of the two curves I'm dealing with. Which, am I dealing with the blue or the red?
Red.
Correct. Let me erase the blue for sure. We know that's not the right quadrants. And the red, I didn't quite draw good enough. I really needed to draw it so it goes through that point. Still hyperbolic. But notice, by just plugging in a value for x, I can figure out whether I'm in quadrant 1 and 3 or 2 and 4. And that's the correct graph. Okay. Now, let's look at 2. We know that 2 is a parabola. Let me scroll down a little bit here. We're going to need a little bit more room. Where's a good place to start? Just follow their directions.
Couldn't you like...
No. Let's figure out where the vertex is. By following their directions, we need the vertex, we need the axis of symmetry, we need the domain, range, x-intercepts, and y-intercepts.
Do you plug it in with 1 to find the vertex?
No, when you're dealing with a quadratic that is not easily factored, and this one is not, you'll notice that this does not factor into an x minus p times an x minus q. So there's an easier way to do the vertex. The vertex is equal to minus b over 2a. That is the x-coordinate of the vertex. So in this case, what is that?
That would be 8 over 4.
Over negative 4.
Okay.
A is minus 2.
Right.
So it's positive 8. In other words, it's negative a negative 8 all over a negative 4. That gives us negative 2. Okay. Now, we haven't solved for the y-coordinate yet. We need to do that. But we immediately know our axis of symmetry. What's our axis of symmetry?
X equals, would it be 4, negative 4?
No, it's always the same thing as your x-coordinate of the vertex. So once you've figured out the x-coordinate of the vertex, that's your axis of symmetry. Okay? So I know that that parabola is symmetrical about that line. And now all I have to do is figure out the y-coordinate. Well, how do I get the y-coordinate of the vertex?
Is that where you plug in 1?
That's where you plug in the x value. In other words, to get the y-coordinate, remember we're going to end up with something like this. And we want to find that spot right there. Well, that spot is determined by an x-coordinate and a y-coordinate. We know the x-coordinate is -2. To get the y-coordinate, go back to the function and find out what f of -2 is. In other words, the y-coordinate is the function evaluated at the x-coordinate.
Oh.
Now let's see, what is that? That is -8 plus 16 minus 4. Looks like 4. So now we know where this parabola's vertex is. It's right there.
Right.
At -2, 4. Okay? That's a lot. In other words, we almost know how to draw the parabola now. Does it open up or down?
Down.
Okay. What is its y-intercept? The next easiest thing to get.
Wouldn't it be just like the normal form of the quadratic?
It's that, no, it's that number right there. Remember what the y-intercept is. The y-intercept is where x equals 0. Well, if I plug in x equals 0, it knocks out the first two terms, and I'm only left with my constant. So I know that there's a y-intercept right there. Now, I got a pretty good idea what this thing looks like. I know that it's symmetrical, so it's got to go through that point. Pardon my art, but that's what the thing looks like. Now, the 2 points that we still have yet to find out, that we don't know, are the two x-intercepts.
Right.
Let me erase some of this stuff I've got here. To figure out the x-intercepts, what's y equal to?
Like for the y, like.
This is a very key concept in math, Sam. You really need to get it down. When you're figuring out the y-intercept, x is 0, correct?
Yeah.
Well, when you're figuring out the x-intercepts, y is always 0. So to figure out the x-intercepts, you set f of x equal to 0. So I'm going to set that equal to 0 and solve it.
Right.
Now,
Use the quadratic.
yeah, I'm going to use the quadratic formula, but before I do, I'm going to simplify it just a bit by dividing everything by -2. And that gives me that. Okay, now use the quadratic formula. Do you know the quadratic formula? You need to always start with the general. I mean, that's the best way to do. That's the best way to do math. Just start writing the general equation and then go back and see if you can plug in everything. So what's the general?
Right. It's negative b plus or minus root root b squared plus minus 4ac over 2a.
Okay, now let's plug in all the numbers and we'll turn that into a number. What's minus b?
Negative 4.
Plus or minus the square root of negative 4 squared is 16. Or excuse me, positive 4 squared is 16. Minus 4 times 1 times 2. All divided by 2. And that appears to be minus 4 plus or minus. That's the square root of 8, which reduces to 2 root 2. And that's important because now I can divide top and bottom by 2, and my answer is minus 2 plus or minus root 2. So those are my two x-intercepts. So this one right here is the negative one. So that's minus 2 minus root 2, comma 0. The y value is 0. And this one over here is going to be minus 2 plus root 2, comma 0. Any questions on everything but domain and range? In other words, we figured out the y-intercept. It was at minus 4. Figured out our two x-intercepts. Figured out the axis of symmetry, and we figured out the vertex, and we've graphed it. The only thing we haven't done is domain and range. So
that's
what's the...
Okay, honestly. We should go to the algebraic. I'm pretty sure we're getting a calculator on the test.
Well, that's okay. Let's just do domain and range. That's real easy. What's the domain? Calculator isn't going to tell you domain.
Negative infinity to infinity.
Okay, and what's the range?
It would be bracket 4 to... Wait, okay, no. It would be negative infinity to bracket 4.
Very good. And it's bracket because it can be 4. It's 4 right there. All right.
Yeah.
Tell me what you want to skip to. On the same page or the other page?
Yeah, I sent you the another document.
Uh-huh. I've got it.
That has algebraic stuff in it. It's just a few months ago I'd forgotten a lot of this, so I just wanted to.
Yeah, no, that's fine.
It's like synthetic division and like
Okay. This has got all the answers on it.
we can like scratch it out and we can just like cover it with like a white paint from your document thing or something.
Okay.
And then we can do it.
I can do that. We're going to start on 1?
Yeah, that sounds good. And then we can just do, yeah.
Now our question is, can I write over the top of that? So, when you do synthetic division, the solution goes in the box. Across the top are all the coefficients, and you have to allow a coefficient for every power of n. So what goes across the top?
Wouldn't it be 1, 3, 14, and 34?
Negative 14.
Oh, right, yeah.
And 34, what goes in the box?
Negative 6.
Now you draw a line there. Now, what's the next step?
Bring down the 1.
Next step?
Multiply it by...
Yeah, now the difference between synthetic and long division is long division is always subtracting. Synthetic division is always multiplying and adding. So I'm multiplying minus 6 by 1. I'm going to put it right there. Then I'm going to add the 2. I'm going to multiply again. I get plus 18. I'm going to add the 2. I'm going to multiply again, minus 24. I'm going to add the 2. my remainder is 10. And it turns out that that remainder is what you get. If I wanted to know what f of minus 6 is, it's equal to that remainder. If that remainder had come out to be 0, then f of minus 6 is 0, and minus 6 would be a 0. There's a rule that says that for a number to be a factor of a polynomial, when you divide that polynomial by that factor, you must get 0, whether we do it synthetically or by long division. And we didn't get 0. So that's fine. That merely says that n plus 6 is not a factor. In other words, if I were to divide this cubic by n plus 6, I would get, what's this 1 minus 3 and 4 mean?
That just means
that's your answer. It's x squared, and we drop down a level because we started with x n cubed plus 4 plus 10 divided by x plus 6. I used x, I meant to use n. But so that's what this number is your answer. Okay?
Okay.
Let's see. Identify the domain of each. Hold on. Kind of like this. It's like a little eraser. Well, I didn't erase enough, did I? In other words, to identify the domain, you want to know where the bottom equals 0, correct?
Yeah.
So this is the question you have to answer. Where is that equal to 0? Well, that factors into x plus 3 times x minus 2. And the solutions for that are x equals minus 3, x equals plus 2. Those are the two values that x cannot be, and those are the only two. So in interval notation, what is my answer?
That would be like those like union to like the lower one.
Okay, let's go left to right.
And then you put the coordinate point.
Hold on, Sam. Let's go left to right, start with parentheses. What's the first thing on the far left?
Negative infinity to negative 3.
Parentheses or bracket?
Brackets.
Parentheses. It cannot be negative 3. Notice that if x were negative 3, I'd be dividing by 0. That's a no-no. You can never divide by 0. In union with what?
Union is negative 3 to 2.
Parentheses or bracket?
Parentheses.
And in union with what?
2 to infinity.
All right. So that's what you have to do to get the domain, is to figure out what x can't be. Okay, let me scroll down here. Divide using long division.
Right, that.
Now, whether you're using synthetic or long, you have to account for every power of the variable. In other words, this has got a b cubed, a b squared, a b that's got every power. If it was missing the b, we would have to allow for it by putting a 0, a dummy thing in there.
Right.
Okay. Oh, man. All right. And the same thing holds true for this. In other words, if I'm going to divide this manually, I've got to divide it by b squared plus 0b minus 8. And I'm going to divide it into that goes down here, minus 3b cubed plus 31b squared minus 49b minus 54. Now, when you're doing long division, the first step of each process, of each iteration, is the same. And that is you divide that into minus 3b cubed. What do you get? What's b squared divided into minus 3b cubed?
Would it be b? 3b?
Negative 3b. Now you take that answer and you multiply it by all three terms. So multiply minus 3b by b squared gives you minus 3b cubed. Multiply minus 3b by 0 plus 0b squared plus 24b. Now, long division is always subtraction. Okay? So when I subtract everything, I get 31b squared minus 73b. I got to bring down my 54, my minus 54, and now I repeat the entire process. Okay? So in other words, I take b squared and I divide it into 31b squared. What do you get?
That would be, what you call it, 31.
Now I multiply the plus 31 by all three terms. 31b squared plus 0b minus 248. Now I subtract. I get minus 73b plus 194. And that's my remainder. In other words, once I get the b down to one level less than my divisor, I'm done. So your answer is, whoops, it's not plus, it's minus 73b plus 194, all divided by b squared minus 8. And that's what your answer should look like.
Okay.
Let's see if it does. Here. This is pretty cool. It's like a... There you go. Minus 3b plus 31 plus, notice the way they've written that.
Right.
And I kind of like the way they did it better than the way I did it. And notice that it's a different number. I kind of like doing it as a plus because then everything goes in as you wrote it. I'm adding that negative 73b plus 194 all divided by b squared minus 8. So I actually made a mistake by not putting parentheses around it and making it a plus. It gives you a slightly different answer. The 194 needs to be plus, and it was going to be minus the way I did it. Okay, on to the next. Number 4 is...
How do you find the behavior again? Is it like an even exponent is like
Not sure what you're saying or asking.
for the end behavior of like of the function?
I still didn't hear that. The audio isn't the best here. What is it you're asking?
Sorry.
Are you asking about problem 3 that we just did?
I was looking at problem 5 with the end behavior.
Okay. End behavior, right-hand end behavior is what does f of x do as x goes to positive infinity? Left-hand end behavior is what does f of x do as x goes to negative infinity? Well, this isn't a hard one to graph. It's just the thing, it's the parabola shifted down by 5 units, right?
Right.
Okay. So what's the end behavior? What does the function do as I go to negative infinity on the x-axis?
On the x-axis.
Yeah, the way you want to look at these is you want to train your eyes to look left, right, or up, down. Don't confuse your eyes by following the path of that function.
Oh,
So,
yeah, I know this.
okay, so when x goes to negative infinity this way, what does f of x do?
It goes up.
Goes to positive infinity. Doesn't just go up. In other words, if I go far enough to the left, that thing will just keep going and eventually it'll reach infinity, okay? How about when x goes to positive infinity? What does f of x do?
It goes to infinity.
Correct. In other words, the end behavior is positive infinity both ways. As you can see from the graph. The graph makes it very clear that it is.
Yeah, that's with the calculator. I'll be able to just graph it.
Okay. Number 4 is a little different of a cubic. It's an easy cubic because it can be grouped. If you can group a cubic, then you always should. She didn't really put the steps in to do this. Here, let me just put in.
You're looking at problem 4, right?
Yeah.
Well, that one I know how to do.
Okay.
Like where you just factor it out and then you make a separate bubble and then you...
But the only reason that you can use grouping on problem 4 is because the ratio of the first 2 coefficients is exactly the same as the ratio of the third and fourth coefficients. In other words, I've got 1 over minus 3. Is that the same as 2 over minus 6? If those are identical ratios, then you can solve it by grouping, which is what they have done here. Make that 6 a 5, and you could not solve it using this technique at all. It has to fit that definition. The first 2 coefficients have to be the same ratio as the second 2 coefficients. Exactly the same. Okay? Then you can do what they've done. And once you get this step, well, now you can factor out the x minus 3 as a greatest common factor. In other words, there's an x minus 3, there's an x minus 3. You're going to take it out, leaving behind x squared plus 2. And then that, of course, turns into some imaginary answers. And those are your three answers. 6 is a whole different thing. However, they don't ask you to solve 6. They just ask you what are the possible rational zeros for each function. Well, what's the formula? When I have a cubic, notice that I can't group this. In other words, 3 over minus 23 is not equal to minus 26 over minus 6. Those are not the same ratios. So I can't group it. And there's only one other possible technique to use when you're working with cubics or quartics, and that is the rational factor theorem, which says what?
You put what you call it?
The constant. Right. If there is a rational zero, if there is, then its numerator has to be a factor of 6, which gives me a lot of choices. If I look at the number 6, it factors into those things. So my numerator has to be plus or minus 6, plus or minus 1, plus or minus 3, or plus or minus 2. Those are my possible numerators. The rational factor theorem also says that the denominator has to be factors of the lead coefficient. It's really that simple. The numerator is factors of the last number. The denominator are factors of the first number, and there's only 2 of them, plus or minus 3 and plus or minus 1. These always have plus or minuses on them. Now, to get the answer, I've got to take all combinations. In other words, I got to consider that as an answer. I got to consider that as a possible answer. So what do we got? We got plus or minus 2, plus or minus 1/3. You with me?
Yeah.
Plus or minus 1, plus or minus 2/3. And then is there any we missed? Yes, we did. We missed plus or minus 6 because we also have to consider this one. And we also have a plus or minus 3. And we got the plus or minus 2 already. So there should be all of our answers, and I think that matches what they got there. There's their 1, 2, 3, 6, 1/3, and 2/3. Which is what we got. We just don't have them in order like they do. Onward.
Yep.
No questions about that technique at all?
That makes sense.
Yeah. Now, if they asked us to solve this, this is the first step, is figuring out all of the possible solutions. In other words, we don't know what the solution is, but I know that one of these numbers is one of them. And so the way you solve this is now you go in and you do synthetic division on each one of these things. There are 12 of them until you get a 0 remainder. And when you get a 0 remainder, you have found your solution, at least one of them. And once you find one, now the rest of it's a quadratic. Because you take that one solution, you divide it into the cubic, and you end up with a quadratic. So you would be able to solve for all 3 zeros using this technique. It's just very, very laborious. It would be like a 20-minute problem because the synthetic division is lengthy, and I've got to try 12 numbers. Now, it may be that all 3 solutions come from this set of 12 numbers. I don't know. Luckily, they didn't ask us to do that, to solve it.
Right.
And if they do give you a problem like that on a test, it'll only be one problem. They'll never give you a test with two of those, because that'd be the whole test. They really do. They are like 20-minute problems.
Yeah.
7.
I get you.
7. The very first step on 7 is to factor out the greatest common factor. Then you're left with a cubic that can be solved by grouping. Notice why. You see why that cubic can be solved by grouping?
Yeah.
Because that ratio is it's 3 over minus 1, and this ratio is minus 3 over 1. That's the same ratio, negative 3 to 1. So whenever you see that same ratio, that means it can be grouped. Okay? And after you go through the grouping process, I think you understand that grouping process pretty good. You can find all 4 zeros. Where'd this 0 come from?
That one, the last one came from the outside term.
That X right there. In other words, what we're saying is that that has to be equal to 0. Well, one of the solutions is X equals 0. And then the other solutions come from handling this cubic. And there's going to be 3 solutions there, and that's that one, and that one.
Right.
Okay, what else?
Let's see which one might be. So 8's just where you plug in like the imaginary numbers.
Find the nth degree polynomial satisfying the following conditions. All right, I think we better do 8. That's not as easy as it might look. Or at least let me talk about 8. Let me erase over here on the left. I'm not going to erase everything she's done there, but I need some writing room, so I'm going to erase this over here. Didn't even know you could do this. I guess I should have figured it out, though. Let's talk about, first of all, the factors. They give us the zeros. If I told, let's go back to the start. If x equal 1, x equal negative 2, and x equal 4. If I told you I had a function that had those 3 zeros, what 3 factors is that?
Sorry, my dad just walked in. What did you say?
If I told you that there was a function that had those 3 zeros on the left.
You plug them in and
how do you convert these zeros to factors?
You make them the opposite sign.
Right. In other words, it would be x minus 1 times x plus 2 times x minus 4. Okay, so that's how you do it. So if you're given the zeros, the first step is to convert them to factors. With me?
Yeah.
Oh, now watch what's going to happen. I'm going to put the eraser on that. Yeah, it's going to bring out everything else. Can't win. All right, I'll just erase that. I'll write over top of it. So here's our zeros. So tell me the 3 factors.
Okay, so you do like 1.
Start from the left, use your pattern, and just go through it.
Wait, you want to combine it, right?
Trying to figure out what she did. I'm a little confused.
Yeah, I don't really understand that.
No, I don't really like what she did. I'm going to erase it because I think what she's doing is confusing.
Wouldn't you just like combine it and then like solve for like?
Yeah, but here's the thing. There's one extra little trick here.
Okay. So you plug in -1 for x and then make it equal to 150.
No.
Okay.
No, not yet. First of all, we got to figure out our polynomial. Well, what's the polynomial going to be? The polynomial is going to be n minus 4, that's one factor, times n minus 2i. And if 2i is a 0, what's another 0 that they haven't given us? Negative 2i. Imaginary factors always come in pairs. So if you have a 2i as a solution, you also have a negative 2i. So there's another factor. And the third factor is going to be n minus 3i, and those also come in pairs. So I need an n plus 3i. Okay? Now, if I multiply all 5 of those together, I get a polynomial. Okay? And here, just to save, that's a lot of math. Hold on a second. I know what this comes to when I multiply it together. I'm just going to write it out for you, and I'll tell you how I figured it out in a minute. It's y equals x to the 4th plus...
Wouldn't it be 3?
No, hold on, hang on. That's what the polynomial comes out to be.
Right.
Okay? Now, they've added, in reality, there's an a in front of all of those.
Right.
In other words, my function could be x to the 4th plus 13x squared plus 36. That has those 3 zeros, or those 5 zeros. She's got the, okay. All right, no, she's got it right. Okay, so, however, any multiple of that function also has those zeros. So, you see this function over here?
Yeah.
That is the function I wrote times 3. And what you get when you multiply these 5 factors together is this right here. But they've said that f of minus 1 has to equal 150. Well, f of minus 1 has to equal 150, which has to equal sum a, that we're going to still figure out, times minus 1 to the 4th plus 13 times minus 1 squared plus 36. If I do that math, I get a equals 3. Now I can take that polynomial that I got, multiply every term by 3, and I end up with that as the answer, which she has over there in the box. But this is a little tricky because it's a difficult concept to understand that. Here, let me draw you what I'm talking about. That function right there has a 0 there, there, and there, right?
Yeah.
And that function is y equals sine x. But I can also draw a function that has the same three zeros. And this function is y equals 2 times sine x. And I could draw another function that has the same zeros that's 3 times sine x. So each of these functions has the same zeros, but they're not all identical. This one's sine x, that one's 2 sine x, that one's 3 sine x. In other words, anytime you find a polynomial that you know it's zeros, then you know that that polynomial could be any multiple of that. So I don't know that x to the fourth plus 13x squared plus 36 is my answer. That's not the answer because f of negative 1 would not be equal to 150. So I have to stick the a in, and I have to solve for a. And when you do that, you get 3 for a. Okay?
Okay.
Let's see, we got about 10 minutes. What else you want to cover here?
Would you be able to just look, is this the whole worksheet? I forget.
Yeah, let me scroll down here. Well, we got more. You have any question on end behavior on 10?
Wouldn't you just like do it, you just graph it?
No, here, let me give you a little clue. The end behavior is only determined by the highest degree polynomial. Only. All the others you can ignore. So end behavior is determined by that only. We're just going to cross those out. Always. Now, is all you got to do is plug in infinity. So the left-hand end behavior is minus infinity to the fourth power. Well, what is that equal to? What's negative infinity to the fourth power? Do the inside first.
Negative infinity would just be like down.
No, don't think of terms up or down. Just treat it like an algebra problem, like that's a number 1 or a number 2. Negative infinity to the fourth power becomes positive infinity. And now I've got a negative positive infinity. So that's my left-hand end behavior. Now if I want to do the right-hand end behavior, still got that negative in front of the x to the fourth, but I'm going to substitute infinity in for that. Now that fourth power doesn't apply that negative sign, that lead negative sign. So again, I've got infinity to the fourth, which is positive infinity with a negative sign in front of it. There's your right-hand end behavior. Left and right are both negative infinity. I suppose that's what these two arrows mean. The left-hand one goes to negative infinity, the right-hand one goes to negative infinity. What else that we're looking at here? 9 is pretty straightforward. It's really where that denominator is 0, and that denominator you just factor it into x minus 3 times x plus 3. That's 0 at 3 and minus 3. So 9 is the easiest problem they've given you yet. On number 9, what if this was a x minus 3 right there? How does that change things?
Like, you cancel the bubbles because it's on the bottom.
But it leaves a hole. It gets rid of the vertical asymptote. In other words, it gets rid of the 3, but you now have a hole at 3. So it doesn't really ignore it. In other words, this is not exactly the same as this. It looks like it is, but it's not. It has a different domain. That's what that thing turns into, right?
Yeah.
But you now have a vertical asymptote at x equal minus 3, and you have a hole at x equal plus 3. So when you can cancel a linear factor from both top and bottom, it doesn't completely cancel. You still have to maintain that domain restriction. And that domain restriction was x can never be 3 or negative 3, no matter what you do to it algebraically. You can never get beyond that restriction right there. X can never be 3 or negative 3. All right. What else?
This all makes sense, honestly. With especially like when I did this before, like this is from the earlier this like year. I wasn't allowed to use a calculator. So
you know, I'm not sure a calculator helps you on any of these. I did not use a calculator one time on doing any of these. Not that helpful. The one thing the calculator will do is it'll let you graph it, and then it'll kind of let you check your answers to see if they make sense. What is that? What is that thing that looks like an M?
I'm not sure, honestly. I forget. Maybe that's like the multiplicity.
Ah, that's exactly what it is. And the reason, in other words, after you factor this, well, now we have that can be 0 or that can be 0, right? Well, this is actually x times x. So that's why it has a multiplicity of 2. Because it's really x times x. Like that. And now either of those x's can be 0. So you end up with a 0 solution, but 2 of them. There's 2 solutions at 0. So that's why it's called multiplicity of 2. Now, in terms of factoring that, let me just give you a quick little secret. Treat that like it is a quadratic. In other words, if I told you this, you'd factor it pretty easily, right?
Yeah.
X minus 4 times x minus 3. Well, this is what I call a quadratic in disguise. In other words, as long as the first term is the square of the second term, you can treat it like a quadratic. And the answer is going to be x squared minus 4 times x squared minus 3. It's that simple. Now, you still have to solve those. So you get x equal plus or minus 2 from that one. Over here, you get x equal plus or minus the square root of 3 from that one. And then you've got the 0 from this one over here. So that's how she gets those answers.
Okay.
You good to go, or you want me to look at the other sheet and see if there's any other thing on there you want to take a quick peek at?
Oh, no, I think I'm good, because the graphing ones, I'll just graph it on my calculator.
Okay. Okay. Yeah, these are pretty straightforward. On number 4, you are going to have a linear factor. In other words, the top's going to factor into an x minus 4, and the bottom's going to have an x minus 4. And that's why one of the things they ask you about is hole, because there's going to be a hole on number 4 here.
Right.
That x minus 4 will cancel one another out after we factor, but it does not diminish the hole. You still have a hole. You lose the vertical asymptote though. So normally you would have two vertical asymptotes of this problem, but because one of those factor cancels out, you end up with only one vertical asymptote.
Right.
And really the easiest way to do all end behavior problems, just plug in infinity like it's a number. I know they don't like to do it that way. Your teacher probably would never do it that way, but it's foolproof. Just plug in either positive infinity or negative infinity. Treat it like a number. If it's being taken to an odd power, then it's still negative infinity. If it's being taken to an even power, it turns into positive infinity. But that's the way to handle end behavior. Just plug in negative and positive infinity for x, and then figure out what f of x does. Sam, I'm going to let you go. Any last questions?
Oh, no, I think I'm good.
Okay. Good luck on your test. I will talk to you later. Bye-bye.